Lesson 717, Distance, Rate, and Time. Today's DLT. By the end of the period, the students will make tables, graphs, and rules, which are equations, relating distance to time for objects traveling at a constant rate. The in-class video you're about to watch covers questions 7-2 to 7-6. The homework for tonight is 7-10 to 7-15. Okay, let's get started. Distance, rate, and time. Question 7-2. You will need to predict how far a car, train, or plane has gone. It would be helpful for you to know something about how fast it was going and how long it had been moving. You will work with your team to investigate the relationship between distance, speed, which is the same as rate, and time in the following experiment. So even though we're not going to do this experiment, we will read through it. Okay. So obtain a meter stick, a toy such as a wind-up car, a long piece of paper, and a stopwatch from your teacher. Again, we're just reading through this. Put the paper on the floor, draw a starting line near one end of it, and place the toy on the edge of the paper facing the starting line as shown at the right. So, you can't see it. So here's the toy, here's the starting line, and there's supposedly the strip of paper. Okay. Place the toy a short distance behind the starting line so that it can reach a constant speed by the time it gets to the starting line. Read the directions below for taking data before starting your toy. It's crooked. Sorry. Directions for taking data. Number 1, appoint a timer, a toy starter, a marker, and a measurer. 2, the toy starter should start the toy. Number 3, as the front end of the toy reaches the starting line, the timer should start the stopwatch. Number 4, when 5 seconds have passed, the timer calls out now. At this moment, the marker makes a mark without touching the toy at the place on the paper where the front end of the toy is. This process repeats at 10 seconds, 15 seconds, etc. for at least 20 seconds or until the toy has reached the end of the paper. Number 5, the measurer measures each distance in centimeters from the starting line. So, because we can't do this in class, I have data from 3 different teams who recorded their information. So team 1, here are their 5-second intervals, and these are the distances in centimeters that their car traveled. Here's the data for, and then there's the accompanying graph. Here's team 2, and here's team 3. Hit focus, okay. So for all case and purposes, we are going to be using the data from team 3. So when I start asking you questions on the back of this paper, know that it relates back to the data given to us from team 3. Okay, let's go to the next page. We hardly wrote anything on that side. All right. This is too large. There we go. It says do a dry run of the experiment one time without collecting data. Then talk with your team about how exactly you will collect the data. Work with your team and take data comparing the time it has passed in seconds to the distance in centimeters that the toy is from the starting line, following the directions above. Obtain a lesson 717 resource page from your teacher. Work with your team to organize your data into a table and graph it. Now remember, we're using the table and the graph on the front side. Be prepared to share your table and graph with the class. Then think about the following questions. Where does your graph begin? Okay, so let's go back and look at this. So where did the graph begin? Right here. What are the coordinates of this point? 0, 0. Do you know the special name of that? Starts with the letter O, origin. So let's put this here. Our graph began at 0, 0, which is also called the origin. Sorry, that was crooked. Okay. Should your graph stop? No. Would it make sense to continue your graph to show how your toy would travel if it were to continue measuring for more time? Yes. If there was more time and space available. You know what, you guys, I need to turn my phone off. Give me a second. Okay. I had to turn my phone off so that we wouldn't be interrupted. Alright. How far would you expect your toy to travel in after 7 seconds have passed? Okay, so I'm going to flip back around. So 7 seconds is right here, in between the 5 and the 10. Can you see that? So then what's in between the 6 and the 13? You know what? Let's do this. After 7 seconds, I would expect it to travel somewhere between there and there. So we're going to say 6 centimeters to 13 centimeters. What about after 2.3 seconds? Well, 2.3 is close to 2.5, which is 2.5, right? So let's go back and look at our table. So if this is 5 and 0 were here, then 2.3 would be somewhere in between there. So if 0, it went 0. What's in between 0 and 6? What's halfway between 0? Sorry. What's halfway between 0 and 6? Right. 3. So it's going to go... I suppose with me in the paper. At least 3 centimeters. Does it make sense to connect the points on the graph? Yes. Why or why not? Well, if you look at your graph, the dots are connected, and the reason being, the toy travels continuously. Continuously. Really sorry, you guys. I feel like I'm writing it really crooked today. All right. Maybe I should move. Okay. What is the unit rate of your toy? That is approximately how far does your toy travel each second? It goes 1 to 2 centimeters per second. How can you see this in the table? It's the difference between the distances one second apart in the table. How can you see it on your graph? The height changes in the graph each second. It's still clicking. What is my problem? All right. Question 4. How can you use your answer in problem 7-3 to write an equation relating the time to the car, relating the time the car has been moving to the distance it has traveled. Let me try something right here, you guys. No, that's not working. It's bugging me that my paper is crooked and this thing's not there. So if I use that as a guide, better. All right. Let me read that again. How can you use your answer in the previous problem to write an equation relating the time the car has been moving to the distance it has traveled? Okay, ready? Let me scoot this up. Distance equals rate times time. Let's write that. Distance equals rate, meaning the speed, times how long it was going that speed. So how far you travel is equal to how fast you are going times how many minutes or how many hours or the time you're going that speed. Okay, number 5. If your toy, God, this is making me insane. Hold on. There we go. If your toy were twice as fast, how fast would it travel each second? Well, we said up here that it went 1 to 2 centimeters a second. So if I doubled that, wouldn't it be 2 to 4 centimeters per second? Because what does doubling mean? It means to times by 2. All right, let's keep going. How would you see this in the table? The distance values in the table would be, let me scoot this up. Would be twice as large. How would you see it in the graph? So when something goes faster, what happens to your graph? Does it lay down flatter or is it more steep? The graph would be steeper. All right. If your toy travels at a constant speed, if your toy travels at a constant speed, then the distance your toy has traveled and the time it has taken are related to each other proportionally. In a proportional relationship, two quantities are related by a constant speed of proportionality. That's called the multiplier because that's the number we're multiplying by. For your toy, the constant of proportionality is also called the rate, which is called the speed. In this case, it's also the speed. Okay, I just wrote that again. Excuse me, this is bothering me. I'm sorry, because I adjusted everything on the table and now I'm having to readjust. Okay, so that concludes our lesson for today. That was a short one, 14 minutes. Okay, so let me just say this. If you haven't been able to download the attachments for each lesson, then at least for the in-class, you can follow along. And then for the homework, do what you normally do. You know, you guys always log into the textbook online and do it from there. Okay? All right. Thank you. See you next time.